So it's a true pleasure to be here at an AI conference, and obviously I will now give you a clinical perspective on how we use machine learning to explore the topics which were just mentioned in the introduction: virulence detection and antibiotic drug resistance. So obviously, as an intro, I don't need to make the audience much aware of what is required for medical machine learning. It's obviously a lot of data, ideally high quality data, and then obviously you also need high performance computers. But is this everything? So what we've observed in the last couple of years is a tremendous access to available data around the globe. And this has mainly to do with the dropping costs of storing data. So obviously what you can see here in the last 20 years or so, the costs to store data were reduced by 1,000-fold. And this results here in this exponential growth of available data. But be aware that the data which we can access around the globe is highly biased. So obviously a lot of data, maybe a third or so, is coming from China. Then you have here the European data sets. This is the Asian Pacific, with Japan excluding China. Then you have the US. And this here, this tiny blue part here, is the rest of the world. So Africa, India, and Southeast Asia. And this is an issue when we talk about generating, for example, AI algorithms, for different countries and different setups. So there is more data available, but there's also biased data available. The second point I want to make in this introduction is that there's an increase in the computational capacity. You can see here actually the first computer of Switzerland, ERMET, which you can visit in Bern in the Communication Museum. It's fantastic to actually go there. It's a fantastic museum. But anyways, I'm not making advertisement here for museums. So what you can see is obviously these chips became much more powerful, and you can see this in this exponential growth of parameters, for example, in neural networks over the time, and we are reaching here 1 trillion parameters. So AI transformed, language translation. We've all faced that with ChatGPT, recognition of speech and images, but medicine lags behind. And why is this? This has something to do with the topic which we are addressing in this session. So healthcare data is highly complex, it's highly dimensional. You need to have curated data on one hand, but you also need the context of the data. So very often it doesn't help you to just say, one word, for example, because a patient, a human being, is very complex, and you need to kind of put this into a broader perspective. The unique features we are looking into, so for example, very rare event. This can be a single point mutation you're looking into, or if you have a data stream, it could be that you have a fever on one day and then this disappears. So how do you actually look for these rare events? Regulatory aspects is an issue which I guess is also addressed during this conference. So for example, the IVDR regulation in Europe, that's the in vitro diagnostic regulation, where also software tools fall under. The expertise, very often in hospitals you do not have AI experts, and the other way around, in data science you maybe don't have physicians around, so you need to find a common language. That's very important. And the last but not least point is obviously the business case, and how do you generate a sustainable business case? And I say this now here maybe a bit ironically, in a broken system, because in healthcare there's not a lot of money in Switzerland. All the university hospitals face tremendous challenges at the moment. So then I basically asked ChatGPT, and maybe I should disclaim this here, what are examples of heterogeneous and sparse data sets? And you can see here a few examples, and I think they are pretty good. So you see here as an example, multimodal AMR data. So this could be, that's a heterogeneous data set. You could have antibiotic susceptibility data, which is phenotypic. You could have genomic data, and you could also have patient data. So that would be a classical multimodal data set. Now, in diagnostics, you can apply AI at various stages. So if a sample comes in, you can process the sample, generate a culture, then you do an identification of the bacteria which are growing on this culture, and then you make an antibiotic resistance testing. And obviously, in all of these steps, as you will see in a second, you can apply artificial intelligence. You can also shorten this process. So, for example, running a PCR or sequencing. Sequencing generates a huge amount of data, and there you can also use machine learning tools. And then, for example, in PCR, you could design primers and test them, for example, with some of these algorithms. So if you actually check microscopy, plate reading, spectral analysis, and prediction, there are a couple of references here. I share my slides so you can look them up afterwards. So there are plenty of publications now in this space around where AI can be used. Now let me focus here first on microscopy. There was a wonderful paper published a couple of years back in 2018 by Ken Smith and colleagues from the US, and what they did is they digitalized images from a microscope. So here is an automated microscope system which grabs actually the slide here in a rack. So this is a rack with different slides, so it grabs the slide, it puts it under the microscope, it autofocuses, and then it microscopes through the slide. And then images are taken, and we use the system, for example, for tuberculosis diagnostics. Now, in this paper, what they did is they trained the system with 180 slides, so not too much. And then you can see here the different features or the different images that they use. So, for example, this is background. Here you can see gram-positive chains. You have here gram-positive clusters, and here you see gram-negative rods. So these are bacteria. And then the machine or the system was trained in a neural network to recognize these different categories of bacteria in the microscope. And so it generated a very good area under the curve, which you can see here. So fantastic. And then they validated that. That's also a very important step with a new data set of 190 new slides. And they assessed the sensitivity and specificity. And what you can see here is that the sensitivity was very good. With one exception, there was a 75% sensitivity to recognize gram-positive pairs and chains. So there was a little bit of an issue, but else the system was very, very promising. Now, I would say in sepsis, this is still a too cumbersome and too slow situation, because gram-positive positive blood cultures you usually have in sepsis, and there a lab technician is simply faster than such a system. But for other microscopy applications, this works very nice, and this is also used nowadays in pathology, as you can imagine. The second example I want to make is culture reading. So if you take a look at the blood culture agar plate, you can see here bacterial colonies growing, and I guess you're not a medical audience, so you would guess, I guess, if I ask you what is this. I can tell you this is a Staphylococcus aureus, and why do I know that? Because I have learned it. So my brain, my neural network kind of memorized that Staph aureus is typically yellow. It has this kind of hemolysis zone around it, and a couple of other features. Now, this you can obviously also do with a convolutional neural network, where you have here the convolution period where certain features are extracted, and then they are allocated in the neural network according to probabilities to a certain species. Now, also this technology is nowadays used in the laboratory routine. So if you have a culture plate, the system can tell you, is there growth or no growth on the agar plate? So it can very rapidly screen if there's a bacteria growing or not, and this is very helpful information if you think about a urine sample where a third of the urine samples are negative, there's no bacteria growing, and then no human needs to look at empty plates, and that's very convenient and increases the quality also. So that works well. What is also working very well is the identification. So based on these features I told you, like certain characteristics, the color, the growth pattern, etc., you can even allocate and say these are certain bacterial species. Now, I was very interested to apply this technology also to fungi. And this is where Lucas comes into place. And here also a big thanks to Sarah, who is also here in the audience. Lucas is a medical student in the 3rd year. And he approached me after a lecture and said, I want to make my master thesis about AI. And I said, yes, why not? And so we thought about the project. And what he did is he took images, 4,500 images with his iPhone of molds which are growing on an agar plate. And there are 161 individual isolates. He took a picture over the growth period of 5 days. So every day he took a picture. And these molds are growing on the plate. They are changing the color over these 5 days. And then he used all this data in different setups. So first of all, there was a baseline setup. So he compared basically 3 different models, a baseline model, then a 6-channel model, and the twin model. And the twin model was the one which worked best. I'm going to show that to you in a second. So basically, the front side and the back side of the plate were used, individual features were extracted, and then that was used for the classification. And you can go through here the details, but I will just highlight the most important point for you. So the area under the receiver operating curve in the twin model reached here an output of 92. And as you know, 50 would be flipping a coin and 100% would be best. So that's a very good first approach. Now, what was fascinating is that obviously the AI also gets better the more and more features are available to learn from. And when a mold is growing on a plate, as I told you, there's color differentiation, there's certain aspects of the mold which also we as a human can recognize, and the AI also has difficulties in the first 2 days. So it's not perfect. For some it works better than for others, but after 3 to 5 days it really gets a very, very nice curve. So you can see here the area under the receiver operating curve, and this is the area under the precision recall curve, and here you have the confusion matrix. Now, how is this performance towards humans? So if you ask a lab technician, at the day 1 or day 2, is the lab technician better? Does human experience now make a difference? And I can tell you, no. So the humans are as bad as the AI. So this is the performance of the AI versus the humans in the first 2 days, basically. But what is very surprising, at day 3 and 5, the AI is better than the human in telling you what it is. And here you have the precision, the recall, the accuracy, and the specificity. So that's very, very interesting, because a lab technician to actually recognize molds on the plate needs years of training, and this was now done during a couple of weeks with a master student. So I'm really surprised about that. The last example I want to give you is on antibiotic drug resistance discovery. The image recognition, which I told you before, also works with inhibition zones. So basically what we do is we take paper discs which are impregnated with an antibiotic, put that on an agar plate, and then the antibiotic diffuses out and it generates an inhibition zone. And this inhibition zone you can read and say if there's an antibiotic drug resistance present or absent. And an AI system can also do this automated reading, and this is a paper which was published here a couple of years ago. Now, as you know, large language models like ChatGPT can also recognize images. And here you see an image of a stool sample. And when you ask, and so that's my favorite joke at the moment when I give an AI lecture, so do you recognize a stool sample? And the ChatGPT actually recognizes that this is a word of play. So it's a joke which the ChatGPT recognizes. But what we did is, in all seriousness, we generated a customized GPT agent. So you can go in GPT-4 and upload certain PDFs and train the system. You're probably all aware of that. So you can upload certain PDFs. So we uploaded experts documents like the breakpoint table from UCAST, some expert opinions on publications, and generated the UCAST GPT expert. And then we shared image data, as I showed you here, where you have a paper disk with an inhibition zone, and we asked ChatGPT, is what kind of resistance mechanism, molecular resistance mechanism is behind it. And the results are mind-blowing. So here you can see the experts, the human experts. You can see here the sensitivity and specificity for a certain type of resistance. It's called ESBL. Here you have AMP-C, that's another resistance mechanism, and the carbapenemase. So the humans are luckily very good. These are medical microbiologists, and so they should know. And then if you check the UCAST expert, the sensitivity are the same, and for carbapenemase is even better. But where it struggles a bit is with the specificity. So it's more careful, it overcalls resistance, and therefore you would go and do too many extra tests to actually confirm the resistance mechanism. But I think it's remarkable that a system like ChatGPT can actually do this. This was obviously anonymized data, and feel assured we are not using ChatGPT in our medical service because it's obviously not an approved software, but it's fascinating what it can do. So the most difficult project, I don't know how many more minutes I have, I think like 10 minutes or so. So the most difficult, the so-called king's discipline maybe for AI is sepsis, because sepsis is an extremely heterogeneous problem. And there are two projects projects which were following each other. There was the personalized Swiss sepsis study and the national data stream focusing on intensive care units, this is still running. And these are two projects which were initiated and funded by the Swiss Personalized Health Network and the PHRT incentive from ETH Zurich. Now, why is sepsis such a problem? Because you have different players. So it's not just the patient, a patient-related problem, because you also have a pathogen which causes the disease. And what is also very important, it's a highly dynamic disease where the timing absolutely matters when you see a patient. If you see a patient, very late, then obviously there are completely different features to extract as if a patient comes in early. And you saw this with the molds, so it's very similar. And time to sepsis diagnostics is very, very important, and time to effective therapy. So what you can see here in this publication is that the survival rate rapidly goes down with every hour a person is in a hypotension situation, so a person in a septic shock. The definition of sepsis is also a bit a problem because it changes. And sepsis is not like a classical disease, it's more a syndrome, obviously, due to the heterogeneity aspects I mentioned before. And there are certain criteria which you have to apply to actually say somebody has a sepsis or not. Now, in Switzerland, we have managed to establish a data framework to explore sepsis. And this is really amazing. The different university hospitals, they have built up during the past years so-called clinical data warehouses. And for every patient who enters an intensive care unit, we collect laboratory values, we collect monitor data from the monitor on the intensive care unit. We have all sorts of data available. This is in the local data warehouse of all the 5 major university hospitals, and this is exchanged towards Leonhard Met, where the data can be accessed for machine learning applications. And in the first period, until 2022, we had 18,000 patients recruited, and that's a lot of data, I can tell you. I think I've not mentioned this on any of the slides, but we're talking here about 70 million temperature measurements as an example, or 200,000 blood cultures which were taken. So it's a lot of data, and it's all interconnected. And that's also very, very nice. I mean, in the project, 46 data concepts were developed, and laboratory medicine, as an example, is one data concept. So all the lab values which these patients have are stored there. And we currently use this to discover new digital biomarkers and predict mortality with a lot of challenges we are facing now in terms of interoperability between the different centers, etc. Maybe that's something for the round discussion then later on. Everybody is taking part of. So we have here the 5 different cities. So from intensive care unit, from infectious diseases, and from medical microbiology, a representative is there. But also we have a lot of wonderful colleagues from data science, Carsten Borgward, Katrin Jutzeler, which are taking part of this endeavor, are also here. So that's my last slide. So here the key messages: integration of AI into healthcare is complex. At each step in the diagnostics, different models may be used. I think that's very important. You saw this now in the couple of applications. We are always comparing different models and try to figure out what is the best one, because I think no size fits all. Most studies are retrospective. This is clearly an issue. I think 95% of the healthcare AI applications so far are retrospective. It's very hard to bring something into a prospective situation where you would, for example, really say the AI decides what to do. People are still a bit reluctant to do that, I guess, also from a regulatory point of view. But this is absolutely necessary if we want to move this field forward. Sepsis management is very, very difficult. As I said to you, I mean, it's a very heterogeneous problem with, sometimes rare events, highly dynamic events, and actionability and sustainability are key. If you generate an AI model, you obviously want it to change something in the process with the patient. And so that's an important goal, I would say. And the sustainability, obviously, to kind of generate a business case is also very important. This whole data warehouse incentive at the moment, I'm wondering how this is actually ongoing in Switzerland, to be honest, because the funding period of this SPHN stops in 2025. So what are the key incentives for the hospitals to invest into IT systems when they can barely afford to build new buildings? And I think that's a very important aspect. And then over-regulation. I'm a big fan, obviously, of ethical work and data protection. I see that this is important, but some of the regulations, I think, are close to ridiculous. And this is an issue because at the end, we want to help patients. And by having so many hurdles to overcome, this is an issue. And we really need to bring together the different stakeholders, because it's also an interest of the patient to have high quality data in healthcare and use this data for the greater good. Okay. So this is my acknowledgement slides. You can drop me an email, but I'm also participating later on in the panel discussion. If you want to collaborate with me, please reach out. We have plenty of diagnostics data, which is ethically not so complicated because it's about bacteria and not about humans. And so this is way easier. And if you're a diagnostic company, for example, please feel free to contact me. Thanks a lot for your attention.